So this is what section questions 1 and 2 are concerned with. So whenever you have a reaction, other than making sure it's balanced, which is one of your other questions, you will have a products. You have reactants and products. The whole thing is called the reaction. But on the left side, you have reactants, and right side, you have products. In order to see how one side compares to the other, you have to use moles. Now, sometimes you can use concentration, which is moles per liter, but that's only when the liters don't change left and right. But many times, for instance, I would add 30 milliliters of something to 40 milliliters of something, and suddenly the liters has changed to 70. So moles is the surefire way. And these questions are all concerned about different ways of getting there. So first they just start you off with moles, and they say how many moles is made when I do this to keep it easy. And then they say, well, how much mass do I need? And you have to use mass with molecular mass to come up with moles. So whenever you have the mass given of a certain substance and you divide it by its atomic or molecular mass, you will get moles. And that's because atomic mass is in the units moles per or grams per mole. And mass in this case should be converted to grams. And when you have a fraction divided by fraction, you get the denominator of the other one as your main unit, which is moles. Conversely, you may have to convert concentration, which is moles per liter, into moles, in which case you have to multiply it by liters to get these two things to cancel. Then you might have a situation where they give you a number of molecules, and then you have to use Avogadro's constant, which is 6.022 times 10 to the 23 with power of 23, which means that there are essentially that many items for every mole. So it would be that number. I'll just use 6.02 per mole. There's billions and trillions of molecules or atoms for every 1 mole. Or, as you've seen from other questions, you might have to use volume. They might tell you there's 50 liters of a gas, and here's the key point, at standard temperature and pressure. Well, then you have to use this ratio. There's always 22.4 liters of that gas for every mole. And then once you convert to moles, you can figure out how much product is created in terms of moles. But you might have to use its molecular mass to figure out how much mass. They might ask you how many grams is produced, in which case you again have to take your moles and multiply by molecular mass. See, that's why they have the multiplication, to get your mass. Or you might have to multiply by Avogadro's constant to get how many particles. Or you might have to multiply by this constant to determine how much volume. So you might have to do both ways. So again, you have to take mass and divide by molar mass to get moles, or particles and divide it by Avogadro's constant to get moles, or volume and divide it by this constant to get moles. But then on this side, you have to multiply. And that's what the mole bridge is called. So all these are using mole bridge. Now, when you're given a reaction like this, you need to notice that it takes 2 moles of NF3 plus 3 moles of hydrogen gas to create 1, when there's nothing there, it's just a 1, mole of N2 and 6 moles of HF gas. Well, that can be turned into this ratio, and it's used depending on what you want. Now, in this case, the question asks how many moles of NF3 will you get, which means you want this constant at the top. However, you will have situations where you have to flip this ratio, and it's going to be 3.3 moles over 2 moles of NH3, and that's in a case where, let's say, they want to know how many moles of H2. But beware, they can ask how many grams of H2, and you still have to use this constant to get over the mole bridge. So you're always going to be figuring out how many moles of this substance per whatever moles that they're asking about. Okay? So in this first question, you need to figure out how many moles of NF3 will be produced, which is, or is needed, rather, 2 moles of NF3 for every how many moles of H2? 3 moles of H2. And that's described in this reaction. But then notice that they ask you an unusual question. I'll go over back to this thing. They're asking you not for grams or anything. They're asking if I take 5 moles, I'm just going to get rid of this. If I take 5 moles, 5.5 moles of H2, which is what's asking here, how many moles, always look at what they want, of NH3 will be consumed? So in this case, we know this ratio, and we know that they want this answer. So that means I want this at the top. I wouldn't use the flip. They've also told me that I have used up 5.5 moles. That's 5.5, so I'll put it a bit over here, of H2, which is not 3. So this is why we have to use this constant. Well, if I multiply this by this fraction, it's clear that these words cancel, and I'm left with these words. So that means I just have to take 2 times that and divide it by 3. So that's 11 divided by 3, and whatever that is, that's almost 4. So it's like 3.66666, which means for every 5.5 moles of hydrogen I consume, I need a corresponding 3.666 moles of NH3. That's what it means. Which makes sense because the ratio here is 2/3. All these questions are like this, except that sometimes it's going to ask you instead about grams, like this question. This one says, I want to know how many grams is produced, which is on this side. If I want to produce this many grams of N2, how many moles of H2 do I need? Well, this is a grams, right? And you have to divide it by atomic mass. So remember this bridge here. If I have mass, I have to divide by atomic mass to get moles. Then I have to use that ratio. So that's what all these questions over and over again. So which means that, just get rid of my scribbles, in this question, I take 180.6 grams, and I have to divide it by the atomic mass, and be careful, it's not of N, it's of N2. Well, that's when you should always have your periodic table, and they'll give you one on the test for sure. And you're going to be familiar with some key items, but nitrogen is one of the common ones, and it's 14. You get used to 14 for nitrogen and 12 for carbon and 16 for oxygen. But there's 2 of them, so it's 28. So you're going to divide this by, and this unit is gram per mole, and you're going to end up with moles. You're going to end up with moles of N2 produced. But then up top, you're going to see that it takes 1 mole. It produces, you need 3 moles of H2 to produce 1 mole of N2. So whatever we get here, which will be roughly, and I'm not going to do the calculations for you, it will be roughly, 30 goes roughly into 180 6 times. So it'll be roughly 6 moles. And then you have to divide it, multiply by 3. It's going to be roughly 18 moles of H2 is needed to produce that many grams of N2. And that's what these are all about. Forcing you to use the mole bridge in different ways. If you completely react NF3, what mass of HF? So now they've added mass to the right side. And NF3 is here, and HF is here. And the ratio is 2 to 6, but you can use a 1 to 6, 1 to 3 if you want, because that's the same as 2 to 6. But anyway, we need the atomic mass of both now. Atomic mass of NF3, and we need the atomic mass of HF. Why? Because they want the mass of both. So really our unknown here is fluorine, and we can see that its atomic mass right there is 19. You can see it right there, 19 in your book. So that means nitrogen, which we already figured out is 14, will have 3 times 19, which is 57. So its atomic mass is 71 grams per mole. Try to always use the units. And HF, we've already know H is 1 and F is 19. So this one has a mass of this per mole. And the reason we use moles is you can see these masses are different things. yet the relationship with their moles is what will react. So we can't use mass. We always have to convert to mole. So that means I have to take, here's the process. I would have to take what mass of HF will produce. Well, I have to figure out how many moles this 17.04 grams is. So I have to divide it by its molecular mass or its atomic mass, which is 71. You can see I'm going to have less than 1 mole. It's going to be roughly 0.2 moles. And now that means I have to figure out what the ratio of NF3 to HF is in the equation, because I want to know NF3. And I can, as we said, it's 2 NF3 for 6 HF. And this was, we figured out here the moles of NF3. I'm going to have to multiply it by 2, I think it was 2 moles of NF, or was it the opposite? Oh yeah, 2 moles of NF3 for every 6 moles of NF3. Oh, wait. Yeah, of NF. I think I've got it all screwed up here. HF. Yeah. So we got to look up here. There's 6 moles of HF for every 2 moles of NF3. So there we go. Now notice that I have moles of NF3 over here. So I don't want it up top because I'm trying to figure out moles of this. So I actually have to flip this ratio like that and use it like this as a fraction, so that the words moles of NF3 will cancel. So it'll be 0.2 times 6, which is 1.2, and then divided by 2, which is about 0.6. Remember that this isn't accurate. I haven't done the division. That's up to you. So that means I have 0.6 moles. Means I have 0.6. Remember, it's not accurate. Moles of HF produced. So moles is no good. I have to multiply that by molecular mass to get the moles. So I have to multiply it by 20, which means I'm going to end up with roughly 12 grams, just as a rough idea, but that's how you do it. And what's this one asking? This one's asking a similar thing. It's saying if 3.56 moles of this thing is reacted, how many liters of this is reacted? You can see it's a 5-to-3 ratio. But they haven't given us 5. They've given us 3.56. So here's what you do. You know that you have 3.56 moles of HBr. I'll just say HBr. And you know that you get 3 Br2 gases, moles of it, for every 5 moles of HBr. So it's clear that these words here will cancel. And it'll be 3.56 times 3 divided by 5. Once you get that, and I'm not going to do the calculations, but it's roughly 9 divided by 5. It's just under 2, so it's like 1.8. Then you know you have that many moles, roughly. Remember, it's not the exact calculation of that. But then you have to use this. There's always 22.4 liters of gas at STP for every 1 mole. So you multiply this, you can see the words moles cancel. And you're left with 1.8 times 22, which is roughly 40 liters of Br2 should be produced. And that's how you do that. Then they do it, notice here, then they ask the number of molecules. In order to produce that many molecules of Br2, how much HBr? Notice they ask for mass. So you have to work backwards. How many moles is that? So you would take that, and you'll know that it's 1 mole for every 6.022 times 10 to the 23 molecules. And if I multiply that by 3.311 times 10 to the 24, the 10s to the 24 cancel with the 10s to the 23, and I'm left with just 10. And this is roughly half. So you get 0.5. This divided by this is roughly half. So you get 0.5, a little bit more than 0.5, 0.55 times 10, which ends up being 5.5 moles. Then you have to figure out how much HBr is produced for every Br2, or how much HBr is needed. Well, it's 5 HBrs are needed for every 3 Br2s according to the formula. So you have to multiply it by this, which is how many moles of Br2 I have. Well, you can see top is roughly 27, and 27 divided by 3 is roughly 9. So you discover that there's 9, and the Br2's cancel, moles of HBr needed. But you're still not done there because they want mass. So that means you have to multiply this by the molecular mass of HBr. So you have to look that up. And then you get your answer. So it's all about using this mole bridge concept over and over again. But sometimes they talk about mass on the right, mass on the left, particles on the left, particles to volume, volume to mass, mass to mass, etc., etc., etc. Eventually they'll hit concentration too, which isn't on here. So we'll get to that. And then finally, the last question. Given the balanced equation here, what mass of this is needed to react with this? Well, here, notice they give you a volume with a concentration. Concentration is just moles per liters, and that 15 milliliters is just 0.015 liters. Well, the first thing you should do is figure out how many moles HCl you're dealing with. And to do that, you have to multiply by the concentration, which is 1.5 moles of HCl per 1 liter. You can see the words liters cancel. And so really you're just multiplying these two things together. Whatever that is. So that'll tell you moles of HCl. Once you have moles of HCl, you look at the equation, you realize that it needs 2 for every 1 mgCO3, you need 2 moles of HCl. So then you find whatever you found as moles of HCl, you divide it by 2 essentially to get your moles of mgCO3. But then notice they ask for mass of that. So now you have your moles of mgCO3, but you want mass, so you have to multiply by atomic mass, and that'll give you the mass. Then they want volume, and you've got grams. So you have to convert these grams to moles by dividing by the molecular mass. That's the magnesium carbonate there. Then you realize that there's 1 to 2 ratio, so you get 2 times as much of this for every times that. So you multiply it by 2. And then, completely racked with this. Calculate the volume of that, okay? And then once you figure out how many moles is reacted with that, you now have to figure out how many moles, and they want to know volume. So you know that volume, that this is 2m, which is 2 moles per liter. So you multiply it by the moles of HCl you just found. No, you don't, sorry. You take the moles that you found in the last moment, and you divide it by this, and you're left with liters. Once you have liters, you'll know how many liters that is, and that's the volume. And you're set. So all these is just the mole bridge over and over again.